Hello and welcome to part 2 of video 1 of feature engineering, dimensionality reduction, feature selection, and feature extraction. In the previous part 1 of video 1 of the same series, we basically defined what do we mean by dimensionality and why we need dimensionality reduction. And we also defined two types of dimensionality reduction. One is known as feature selection and one is known as feature extraction. Just reviewing briefly, feature selection means just select a few features from the original features, and feature extraction means construct a few new features from the existing features. In this particular video, I'll be talking about feature selection. We will be talking about feature extraction in video 2 completely. So in this part of the video, which is part 2 of video 1, as well as part 3 of video 1, we will be primarily focusing on feature selection. In video 2, the three parts of video 2, we will be focusing on feature extraction in detail. So in this video, I'll be first explaining why feature selection, why it is important, and then I'll be discussing methods of feature selection. So let's start by answering basically the question, why feature selection? The question is important because there is a feature extraction module as well. So one may tend to think, why don't we always construct new features, a few of new features from existing features? Why really we need to keep the identity of the original features? Why feature selection at the end of the day? So the question can be answered in several ways. For example, in some cases, whether we are doing feature selection or feature extraction, the goal eventually is to help the machine learning model perform better. So we have some machine learning model, just assume a classification model, some model like SVM or logistic regression or some deep neural network. We have some machine learning model. And this dimensionality reduction is a phase that actually we get an X, which is the data. We reduce the dimensionality of it, sometimes X and the labels as well, if the classification data. And we have this X new, let's say, and Y, and we give that to machine learning model. Sometimes we really want this machine learning model to be interpretable, or we really want to know what features actually lead to a particular performance. Sometimes we also know what features they are highly correlated with the target label. So in several cases where the interpretation is required, and we need to know that a particular machine learning model is basically depending upon what subset of features are important in defining the class label in terms of classification, or the target in general in terms of regression as well. So the interpretation really becomes handy in terms of feature selection. If we change the features and get new features, like we do in feature extraction, we actually lose the identity of the original features, and sometimes the interpretability of the machine learning model becomes really hard. So wherever certain interpretability of machine learning model is required, where we want to really rank certain features to be more important than the other features that lead to a particular label, class label, or the target label, we really need feature selection rather than feature extraction. And there are several cases where this feature selection really becomes important. So let me give you an example on some of the data sets in Python. Let's, for example, load import pandas as PD, import, let's say, seaborn as SNS. Also, let's import numpy as NP, may be required somewhere. Then what we do is let's say we load iris data. Iris is sns.load data set and iris. That's the data set. If we see iris.head, then we'll be noticing that there are basically the dimension of this data is really 4, where the last attribute is really the class label. That's a classification data. So we have attributes or variables as sepal length, sepal width, petal length, petal width, and then we have some species where the different types of species are, for example, iris dot species dot unique. If we see all the species, so one species is setosa, then we have versicolor, then we have virginica. Now we might be tempting to think about maybe this is the sepal length that defines the species very well. Maybe that's a sepal width. Maybe that's a sepal length and petal length. Maybe the width is not required. Or maybe it's a sepal width and petal length. Maybe it's alone petal width. So sometimes we really want to interpret these kind of features. What feature or what subset of features really lead to defining the target label? In those kind of areas, we really need feature selection. And let me give you another example where let's say let me give you an example of some real data. Maybe I have some real data somewhere. Yeah, video 1. Yeah, this data. So that's the accent recognition data, where you need to recognize the accent of different people, whether its accent is so the accent fall in what kind of category. So let's load this data. Let's df is pd.read csv, and then we have this r for raw reading, and yeah. So let's say we have df.head, and here we have this data with for example, let's see, that's language, that's the accent or language, that's the class label, and then we have 12 variables or 12 features, x1, x2, x3, x4, and these are 12 of those. Here let's see how many different target labels we have. df.language .unique. So let's see how many are these. So there is ES, FR, GE, IT, UK, and US. So basically there are 6 of those. So we want to categorize based on these 12 values, x1 till x12. We want to categorize what is the accent. And these are some features. Maybe we do not know what this x1 really is describing, what this x2 really is describing. Maybe in some cases we know, and we want to keep their identity. But maybe in some cases we do not know what x1 really describes, what x2 really describes, what x3 really describes. All we need to know is, given x1 to x12, we need to categorize the accent. In these kind of cases, we may tend to use feature selection to pick some of the features that are highly descriptive in terms of the accent. But we may tend to construct new set of features by not keeping the identity of the original features to describe the accent. So wherever we really have a problem of interpretation, what kind of features lead to what kind of result, feature selection is the goal. And in certain situations this is required. Where this is not a condition, wherever the interpretation of certain features or model is not really a larger goal, we may use feature selection, or we may tend to use feature extraction instead. So so next we in the rest of the video we'll focus on the 3 main feature selection methods. One is known as filter method, another is known as wrapper method, and one is known as embedded methods. So let's dive in to see each of these feature selection methods, the merits and demerits of each of these methods one by one. So let's see. Let's start by filter methods. A filter method actually, by the way, all these methods, they can be a single feature selection methods or a subset feature selection methods. So in filter methods, what happens is there is a certain criteria whatever criteria, let's say the criteria, let's say we have some features, let's say x1, x2, and xd. These are the features. And let's say we have a target label or the class label y, assuming the classification data. Filter methods actually selects different features individually, sometimes individually and sometimes based on the subsets, based on a certain criteria. One criteria might be correlation. So maybe x1 is selected as an important feature, if x1 is highly correlated with the target, with y. We may, for example, compute the correlation of x1 with y and see whether the correlation is high or not. There's a way to compute correlation. There's a simple way to compute correlations. If we are using correlation criteria, I'm just giving an example. And then we can compute the correlation of x2 with y and then x3 with y. And let's say we want to select out of these D features, let's say we want to select just 10. Let's say we want to select 10 features. So what do you think? What is the way to select 10 features out of these D features? Well, one way is if you build a correlation criteria, you can just rank all these features based on the highest correlation to lowest correlation, and then you pick the top 10. That's one way, and the filter methods do that. You can change the criteria, for example, from correlation to some other criteria, maybe information gain, or there are several criteria you come up with that actually, based on whether you are going to keep the correlation, you're going to keep the entropy or information gain of different features and stuff like so. So in filter methods, you have a particular criteria. So you have a particular criteria, let's say criteria is C, whatever that criteria. You fed your data X, Y, and you rank your features individually based on those criteria. And you select the new features, maybe a few of those, maybe you want to select 10 of those. So what 10 have this criteria maximum? Filter method does not work only for individual cases. You can have a subset of features, and you can have the criteria on the subsets rather than individual. For example, one subset is I'm given D features, and I want to select a subset of, let's say, K features, maybe X A1, X A2, and X AK. Maybe I want to select K features out of those, such that this subset preserves the original geometry of the D-dimensional features. So original geometry is sometimes can be described as the pairwise distances, maybe. So maybe we want to pick a subset that preserve the original geometry or the submanifold structure of the data, and that might be a criteria on a subset rather than individual features. And then once we set this criteria, the next problem is how to find out this subset, and there are ways to actually select this subset based on incremental ways or a batch mode ways. There are several ways. So in filter methods, we have a criteria, we set that criteria, whether we rank the features based on individual feature rankings, or we may rank the subsets based on subset criteria. So these are filter methods. In contrast, in the wrapper methods, what we really do is we assume a machine learning model as a black box model. Maybe let's say the task is classification. Let's say we may assume an SVM model. So let's say that's our model. What we do is we give different subsets of data. Let's say XA1, XA2, XA3, xak. We supply this subset and see the performance of this model on this subset. Obviously, in the start, we have some training data, and we split the training data in two parts, which is the training data and the validation data. So we have original data available with all labels. We split the data in training and validation parts. And then we actually select the subsets of features over which the any machine learning model that performs the best. And we evaluate the performance on the validation data. Now here there's another issue. What machine learning model really we should use to select these subsets, and how these subsets are being selected? Well, in literature, people say that these machine learning models, whether you are going to do a classification task at the end or a regression task at the end, this machine learning model at the end is a black box. We really choose one of these models, or maybe we choose several of these models and apply cross-validation and select the subsets. So which model really is to choose is really not necessarily fixed. We can choose one model, or we can apply the subset on several models and may pick the best subset based on majority vote of several models. The next question is how to build this subset. Well, one way is forward selection. That's a greedy way. Forward selection. How it works is the following. Let's say the model is SVM. What you do is you supply the first feature in SVM, just train the SVM on just feature X1 and check the performance on the validation data. Then you train it on X2 alone, then you train it on X3 alone, and you train it on XD. So you basically have D different trainings. In each training you have only one feature on which the model is trained. And for each training you actually evaluate the model on the validation data. So in this phase we select one feature that has the highest performance, maybe that has highest accuracy or whatever metric we set. Let's say that feature is X3, let's say. So next what we do is, in greedy way, we incrementally add X1 with X3 and supply these two features and train SVM, then evaluate on validation data. Then we combine this X3 with X2. So we make all the pairs with X3 fixed. So we make all D pairs with X3 fixed. So then we will pick the pair that has the best performance on the validation data. So let's say that is X3 and X10. What next we do is we actually apply X1 with this pair fixed. Then we train on X3, X10, X2, and all these. So we build a triple. So let's say we want to select, for example, 10 features. So this way we will be building incrementally, which is gaining the best performance. In general, this incremental forward selection does not guarantee the optimal selection, but in several realistic situations it works very well. The other way of building this subset, the greedy way, is backward selection. In backward selection, what we really do is we train the SVM on the whole data, for example, X1, X2, XD. By the way, this SVM, I have just fixed SVM. You can have any machine learning model. We train it on all data, we check the performance, and then we drop one of the features. Maybe we drop X1 and train on the rest. Then we drop X2, just X2 alone, keeping X1 and all the rest. So we have basically D trainings, and we will see, okay, which feature we can throw without losing the performance. So we will throw that feature. Then in the next phase, one feature will be thrown out, and then we will repeat the process and we'll throw one more feature. And then we will repeat the process and we'll throw one least important features, and so on. So whether you do a forward selection or backward selection, both are greedy approaches. And in this particular case, a machine learning model is used as a black box to guide which subset is performing well, as in contrast with the filter method, where we do not use any machine learning model that guides the selection process. Rather, we used a particular criteria independent of any machine learning model. In embedded methods, however, we do not need a train test split. We do not need a train and validation split. We do not need that. However, the model is the machine learning model. We first select a machine learning model, and in the training phase of the machine learning model, the features, there is a mechanism to rank the features automatically. Rank features. So there is a mechanism in certain machine learning models that can rank the features if you deploy that kind of model. One such way is regularization. So for example, when you regularize a particular model, let's say you regularize SVM, support vector machines, with L1 regularization, for example, then L1 regularization will give weights for different features, and the weights that are really small indicate that these features are less important as long as you're using SVM with L1 regularization. The other, or you can use, basically all the methods that are regularization based method, they fall under this embedded method, and the regularization actually puts weights on different features, and the weights with whatever features with smaller weights, they can be considered least important. The second way is kind of decision tree models. Decision, whatever the spellings are, decision tree models, COT tree or AdaBoost or something like so. I mean, these kind of algorithms, they actually start weighting the features by keeping the most important feature threshold, then keeping the rest of the features thresholding, and all that stuff. Not always the thresholding works. Actually, there can be weak classifiers that actually select one feature at a time. But in this way, you select the features in hierarchical manner, and different features, they can be ranked depending upon in the depth, what depth or what level of the decision tree they appear in. The only problem with embedded features, embedded methods, are the features that are ranked using an embedded method actually is tied up very strongly with the model. So for example, you select features by using SVM L1 regularization, and you select some of those features using this model. Then using those selected features with some other model other than SVM may not work very well, and that's why the name is embedded there. You select the features, but those features, they are embedded, or they are tied up very strongly with the model that actually was used to select those features. In contrast to wrapper methods, where this is a black box, is more generic, and you can select the features maybe by cross-validating on several models and then picking the best subset based on the majority vote. And these selected features are more generic, and they are not strongly coupled with any model. And the filter method is the most generic one, where there is no concept of machine learning model. We just go and pick a particular criteria and select different features with respect to that. So yeah, so these are the three methods: filter methods, wrapper methods, and embedded methods. In this particular video, I just talk about very briefly the theory of these methods. So there might be a need of practicing these kind of methods in Python. So yeah, I know that because once things are coded in Python or in some programming language live, things make much more sense than theory in general. So in the next video, we are basically going to give you example of live coding of all these methods, including filter methods, including wrapper methods, and including embedded methods. So hope to see you the next part of this video, which is actually the implementation of the filter methods in the library scikit-learn. Hope to see you in part 3 of video 1.